a cube structure was designed by a domain expert in CAD Nano. After converting it into XDNA format, it looks like this. However, it didn't form in the experiment. We performed molecular dynamics simulations to examine the stableness of the structure in various temperatures. We observed in our tool, SynopFrame, quite interesting phenomena at 78 Celsius. In this schematic 3D view, we can immediately perceive a prominent pattern of the hydrogen-bound status at the beginning of the simulation. The pattern shows the middle of the cube disassembles the first. Looks like being cut by a knife right in the middle. If we attach a highlighter to the disassembled nucleotide, the cause of such a pattern can be then concluded from the combination of schematic 3D and schematic 2D that there are many short double helices aligned at that knife-cutting-like plane. This observation can be further easily mapped back to the original CAD Nano design view. The actionable insights are the structure designer needs to fix those short helices, and the CAD Nano developer needs to highlight those and let the user solve them with ease. An RNA tile was known to have two conformations existing together in the experiment. From a simulation at 45 Celsius, the two groups of conformations are well manifested in the principal component analysis plot. Further examination reveals that hydrogen-bound status is not always correlated with the structural reduction. For example, these two conformations are very close to each other in the PCA plot, but their hydrogen-bound status shows a big difference in this critical crossover. This observation raises a caveat that although in general PCA followed by clustering performs well in categorizing the conformations, it cannot reliably capture the subtle hydrogen-bound changes that will cause a huge effect on the conformation change. The transition period can be easily identified. The biggest difference between the two conformations is the loss of these two crossovers. So we can attach a highlighter to this helix and then focus on the schematic 2D, which is much easier to absorb the hydrogen-bound status changes. But the schematic 2D view first shows the opening of another helix from frame 601 to 607. So it forces the analyst to go back to the 3D structure and think about the relation between these two helices. Only after this helix opened, the initially attended helix is then opened at frame 1181 to 1184. The analyst may then proceed to crop out these frames as well as those frames surrounding them to perform further detailed analysis such as distance, angle, and energy distribution. Looking at this bizarre schematic 2D view, one might wonder what these nucleotides are that are not forming helices. A close examination from the linked view with the help of the highlighter reveals that, apart from the non-pairing loop on the sides of the structure, there are 6 base pairs that are in the hydrogen-bound distance, but their sequences do not obey the Watson-Crick rule. The designer might then proceed with changing some of the sequences on those base pairs and see how the design behaves. All the above analyses are done in our new tool, SynopFrame. It has 7 linked viewports and a controller panel. The traditional all-nucleotide structure is shown and then abstracted to the snake view, showing the center of mass positions. Then, the schematic 3D view showing the structure in its designed geometry, the schematic 2D view showing the double helices, the hit bar view showing the strands, the progress bar view showing the progress of the assembling or disassembling. We categorize the hydrogen-bound status into a new format to allow us to color encode it and overlay it on the representations. Other properties can also be encoded in the same format and shown as a color overlay. A conventional PCA plot is also generated and interactively linked with all other views. The default color coding in the PCA plot shows the time, but other properties such as the total energy of the structure can also be plugged in. We also introduce a synchronized highlighter across all structural views to help viewers to locate a specific nucleotide to tackle the challenging clutter and occlusion problems. Any panel can be maximized to use the whole display. We set a control panel to allow users to change the global color scheme between strand identity, hydrogen bond status, and customized properties, to change the layout to adapt to the display size, to highlight the strand or nucleotide by its index, and to achieve a handful of other functionalities. We also implemented the transitions between the representations that have spatial differences to lower the cognitive load for the user to comprehend them so as to understand the structure.